Welcome to Quantum Realms Explained. Today we're diving into a pivotal moment in physics, the photoelectric effect, and Einstein's groundbreaking concept of light quanta. This phenomenon challenged classical physics and paved the way for quantum mechanics. Have you ever wondered how solar panels work, or why certain metals emit electrons when light shines on them? The answer lies in the photoelectric effect, a phenomenon that puzzled scientists for decades until Albert Einstein provided a revolutionary explanation. At its core, the photoelectric effect describes the emission of electrons when electromagnetic radiation, such as light, hits a material. These emitted electrons are called photoelectrons. The photoelectric effect was first observed in the late 19th century by Heinrich Hertz and later investigated by others. However, classical physics, which described light purely as a wave, couldn't fully explain its peculiar characteristics. Classical wave theory predicted that the energy of the emitted electrons should depend on the intensity of the light, and that electrons would eventually be emitted regardless of the light's frequency, given enough time. However, experiments showed something entirely different. Electrons were only emitted if the light's frequency was above a certain threshold, regardless of how intense the light was. Below this threshold, no electrons were emitted, even with very bright light. Furthermore, the kinetic energy of the emitted electrons depended only on the frequency of the light, not its intensity. More intense light simply meant more electrons were emitted, but their individual energies remained the same. This was a major paradox for classical physics. In 1905, in one of his Annus Mirabilis papers, Albert Einstein proposed a radical solution to the photoelectric effect. He suggested that light isn't just a wave, but also behaves as if it's made of discrete packets of energy, which he called quanta, or photons. Imagine light not as a continuous ripple, but as a stream of tiny individual particles. Each photon carries a specific amount of energy, proportional to its frequency. Einstein's famous equation for the energy of a photon is E equals hv, where E is the energy, h is Planck's constant, and v and u is the frequency of the light. This equation was key to understanding the photoelectric effect. With the concept of photons, the photoelectric effect suddenly made perfect sense. When a photon hits a metal surface, it transfers its entire energy to an electron. If the photon's energy is high enough, i.e., its frequency is above a certain threshold, it can knock the electron out of the metal. The minimum energy required to remove an electron from a metal surface is called the work function. If the photon's energy is less than the work function, no electron will be emitted, no matter how many photons hit the surface. This explains the threshold frequency. Einstein's photon theory was initially met with skepticism, but soon, experimental evidence overwhelmingly supported his revolutionary ideas. Experiments by Robert Millikan, among others, precisely measured the relationship between electron kinetic energy and light frequency, confirming Einstein's predictions with remarkable accuracy. This solidified the quantum nature of light. The photoelectric effect has numerous real-world applications. It's the fundamental principle behind solar cells, which convert light energy into electricity, and photodetectors used in cameras, optical sensors, and even automatic doors. The photoelectric effect and Einstein's explanation of light quanta marked a turning point in physics. It demonstrated that light, previously thought to be purely a wave, also exhibits particle-like properties. This concept of wave-particle duality is a cornerstone of quantum mechanics. Einstein's work on the photoelectric effect, for which he received the Nobel Prize in Physics in 1921, didn't just explain a puzzling phenomenon. It opened the door to understanding the quantum world, forever changing our perception of reality.